Welcome to WikiPodcast.
And welcome to the deep dive.
You brought us a really fascinating stack of sources today. We're looking at something pretty fundamental, maybe even a bit mind-bending, the philosophy of physics.
That's right. This deep dive is really about seeking truth, not just in physics, but maybe underneath it. Because physics, well, it's not just equations in labs, is it?
No, not at all.
It bumps right up against these huge questions about what reality is.
Absolutely. You push the science far enough and suddenly you're doing philosophy. So our mission today, looking at these sources, is to really unpack the big conceptual questions, the interpretational issues right at the heart of physics.
Yeah, we'll touch on some massive ideas, things like space-time, the weirdness of quantum mechanics, even thermodynamics, heat.
Okay, so let's start with the basics. According to the material, what is philosophy of physics exactly?
Well, it's defined basically as the field that tackles those conceptual and interpretational puzzles that come up from physics itself.
And I guess it must overlap quite a bit with theoretical physics sometimes. Seems like they're asking similar deep questions.
They definitely do. I mean, historically, this field has always been asking things like, what is space? What is time? What's matter? What are the laws governing everything?
Right, and digging into how we even know these things, the epistemology and what actually exists based on the physics, the ontology.
Exactly. And it draws on all sorts of philosophy, metaphysics, epistemology, philosophy of science generally. But crucially, it has to engage with the latest physics, the cutting-edge stuff.
Because the physics keeps throwing up new puzzles.
Precisely. And its purpose, it's about conceptual analysis, really.
Yeah.
Clarifying foundations, trying to figure out what the theories imply about the world, and sometimes, even guiding how new theories might develop by pointing out the conceptual snags.
Okay, makes sense. So let's dive into some key areas your sources highlight. First one, the philosophy of space and time. Seems like a natural starting point, but I have a feeling it gets strange quickly.
Oh, it does. The big questions are, do space and time actually exist fundamentally? What are they? Are they like a background stage, or do they emerge from something deeper?
And how are they different operationally?
Let's take time. For ages, the view was pretty simple, right? Like a river flowing the same for everyone.
Newton's absolute time. Fundamental, ticking away uniformly everywhere.
That was the standard picture until the 20th century. Then Einstein, Minkowski, relativity, it all changed. Time isn't absolute. How fast it passes depends on your frame of reference, how you're moving, gravity.
So my now isn't necessarily your now if we're moving differently.
Exactly. Relativity makes that idea of a universal, privileged present moment much harder to sustain. It's frame dependent.
Wow. So not just one river, but like lots of different currents.
That's a good way to put it. And some theories now, really out there stuff like loop quantum gravity, suggest space-time itself might not be fundamental. It might be emergent.
Emergent, meaning it arises from something more basic.
That's the idea. Carlo Rovelli had that striking quote, "No more fields on space-time, just fields on fields." As if space-time itself is built from other things?
Huh. So time, as we experience it, might be like a side effect of deeper physics.
Possibly. I mean, today, how do we define a second? It's based on the vibrations of a cesium atom. Super precise, tied to a physical process.
And we use that combined with space and mass to define velocity, energy, all that.
Right. And, general relativity plus observations like cosmological redshift points to the universe. And maybe space-time itself having a beginning. The Big Bang, roughly 13.8 billion years ago. So time might have started.
Okay, what about space then? Classically, that was fundamental too, right? A big 3D grid.
Yep, 3D Euclidean space. Fixed container, you locate things with 3 coordinates moving through it as time passes.
And again, defined by measurement, the meter, based on how far light travels in a vacuum, in a tiny fraction of a second.
But relativity shook that up too. It wasn't 3D space and 1D time anymore, but this unified 4D space-time. They're tangled together.
And some theories even play with more dimensions.
Oh yeah, some speculative physics explores ideas with more than 3 spatial dimensions, so even the number of dimensions isn't necessarily settled.
Okay, space and time are already shaking my foundations, but I suspect things get even weirder when we turn to the philosophy of quantum mechanics. Your sources say this is a huge focus now.
It absolutely is. I mean, the core challenge is just making sense of it. QM is incredibly successful at predicting things, but what it seems to imply about reality is just bizarre. Superposition, for instance.
Where particles seem to be in multiple places or states at once.
Exactly. Until you measure them, it flies in the face of common sense, our basic metaphysical picture of the world. The goal is to figure out what the math, which works so well, is actually telling us about what's real.
So where do the philosophical problems start? The uncertainty principle is a big one, right?
It's one of the first big conceptual hurdles. It's fundamentally a mathematical limit. You can't know both the exact position and the exact momentum of a particle simultaneously with perfect accuracy. There's a trade-off.
And it came from trying to picture electrons as waves, because waves don't really have a single precise spot.
That's part of the origin story, yeah. It points to a fundamental limit in applying our classical concepts to the quantum world. And that limit made people like Einstein wonder, is the theory missing something? Are there hidden variables?
Which brings us to locality and these hidden variables. Can you break those down?
Sure. Locality is just the intuitive idea that things are only affected by their immediate surroundings. No spooky action at a distance faster than light. Hidden variables would be some underlying properties, not described in standard QM, that actually determine the outcomes we see, like hidden gears setting the results beforehand.
Right. And then John Stuart Bell came along and did something revolutionary.
Absolutely game-changing. Bell proved, mathematically, that if hidden variables exist and they are local, meaning they obey that no faster than light influence rule, then there are limits on how strongly correlated the measurements on separated entangled particles can be.
Entangled particles.
Yeah.
One's linked in that weird quantum way.
Exactly. The ones from the EPR paradox thought experiment. Einstein, Podolsky, and Rosen imagined preparing two such particles, sending them far apart, then measuring one. Measuring particle A seemed to instantly fix the state of particle B, no matter how far away it was.
Which Einstein called spooky action at a distance.
He hated it. EPR argued this meant either there was spooky action or QM was incomplete, because the outcomes must have been predetermined by local hidden variable all along. They bet on incompleteness.
But Bell showed that the local hidden variable idea had testable consequences.
Yes. He derived an inequality, the Bell inequality, that must be satisfied if local hidden variables are the explanation. But quantum mechanics predict correlations that violate this inequality. They predict stronger correlations than local reality allows.
So you can test it.
You can. And people have many times in increasingly sophisticated Bell tests. The results are incredibly consistent. Physical systems behave as QM predicts. They violate the Bell inequalities.
Meaning, local hidden variable theories are ruled out.
That's the standard conclusion. It seems we have to give up either locality, allowing some form of faster-than-light connection, though not for sending information, or realism in the classical sense, the idea that particles have definite properties before measurement, or maybe even other assumptions Bell made. It forces us to accept that the quantum world is profoundly non-classical, non-local in some sense.
Wow. Okay, that deepens mystery. So if QM is so weird but correct, how do people try to interpret what it means?
Well, that's where the different interpretations come in. Because it's so counterintuitive, people have developed different ways to sort of tell a coherent story about the reality QM describes.
Like the Copenhagen interpretation. That's the classic one, right? Associated with Bohr and Heisenberg.
It is. Copenhagen generally views QM as intrinsically probabilistic. The Born rule just gives you the odds of finding a certain outcome upon measurement. It talks about complementarity. Some properties, like position and momentum, are paired in a way that you can't know both precisely at the same time.
And measurement is key.
Crucial. In this view, measurement is an irreversible process that somehow collapses the possibilities into one definite outcome. Before measurement, it's not quite right to say the particle has a definite position, for example. Quantum descriptions are objective, but reality becomes definite only through measurement.
Okay. Then there's the many worlds interpretation. Hugh Everett's idea. This one sounds wild.
It is a radical departure, many worlds says. Take the math, the wave function, absolutely literally. It describes reality. And crucially, there's no collapse of the wave function.
No collapse. So what happens when you measure something with multiple possible outcomes?
According to MWI, all outcomes happen. The universe, or the reality described by the wave function, branches. There's a branch, a world where you got spin up, and another where you got spin down. Both are equally real.
So infinite parallel universes constantly splitting off.
That's the popular picture, yeah. It stems from taking scientific realism very seriously if the theory works. Maybe its description of reality is literally true.
But wait, QM looks probabilistic. We get definite odds. If everything happens in many worlds, where do the probabilities come from? Isn't it deterministic?
That's a major conceptual challenge for MWI. The underlying evolution is deterministic, yes. Proponents argue you can recover the appearance of probability, maybe through decision theory or analyzing the structure of the branching, but it's a really debated point.
And can we tell these interpretations apart experimentally?
That's the kicker. Mostly no. Especially once decoherence happens, the process where quantum systems interact with their environment and lose their obvious quantumness very quickly for large objects.
So it becomes practically impossible to distinguish.
Right. Your source quotes Roland Omnez, calling it a great chasm. He says MWI restores almost everything we think of as reality objects, properties, every feature except one, the uniqueness of facts. In MWI, the outcome you experience isn't the only outcome that happened.
Mind blown. Okay, let's shift gears slightly. Another area mentioned is the philosophy of thermal and statistical physics, heat entropy.
Yeah, this deals with thermodynamics and statistical mechanics. How does the large-scale behavior of stuff like gas in a box or an ice cube melting emerge from the countless tiny particles that make it up? And it tackles emergent laws like irreversibility and entropy always increasing.
And this is where the famous arrow of time problem lives.
Exactly. It's a fundamental conflict, or apparent conflict. The basic laws governing individual particles, whether classical or quantum, seem to be time reversible. They work just as well forwards or backwards in time.
Like running a movie of billiard balls colliding backwards, it still looks like a plausible collision.
Precisely. But in the macroscopic world, things clearly have a direction. Eggs break, they don't unbreak. Heat flows from hot coffee to the cool air, never the other way around spontaneously. How does this observed irreversibility arise from underlying reversible laws? That's the puzzle.
And similar to QM, there's a debate about probability here too.
Yes, a big one. When we use probabilities in statistical mechanics, like the probability of finding gas molecules in one half of a box, are those probabilities epistemic, meaning they just reflect our ignorance? Or are they onseictic, objective features of the system itself?
So epistemic means we use probability because we just can't possibly know the exact state of every single molecule. It's a practical tool for dealing with complexity and lack of knowledge.
Right. It's subjective in a sense arising from our limitations.
Whereas the ontic view says,
The ontic view says the probabilities are real, physical properties. The probabilistic nature is intrinsic to how these large systems behave, not just a reflection of what we don't know. Even if you could know the microstate perfectly, the description would still be fundamentally probabilistic at the macro level.
it really echoes that QM debate. Is the randomness in the world, or just in our description of it?
Very similar philosophical terrain, yes. Questions about reality versus knowledge.
It's helpful sometimes to see how these ideas developed. Your sources briefly touch on the history, Aristotle to Newton to Leibniz.
Right. We went from Aristotle's picture universe as a sphere, elements having natural places, motion as just changing place.
Seems intuitive, but maybe not very predictive.
Exactly. Then Newton blew that away with his laws of motion, especially inertia. Things keep going unless forced, no natural place or motion. And crucially, he believed in absolute space, this fixed, infinite 3D grid, and absolute time flowing independently.
He needed that fixed background for his laws to make
You
sense.
feel he did, yeah. To be at rest meant being at the same spot in absolute space.
But his contemporary, Leibniz, disagreed.
Strongly. Leibniz argued space, time, motion, they're all relative. They describe relationships between things, not an absolute background container.
But he was way ahead of his time on that, anticipating relativity.
Remarkably so. The source quotes him. I hold space to be something merely relative as time is, an order of coexistences, as time is an order of successions. He saw them as relational structures.
So that fundamental debate, absolute stage versus relative relations, has been going on for centuries and feeds right into modern physics.
Absolutely. It's an ongoing conversation.
Wow. We really journeyed through some deep waters here. The nature of space and time, maybe even their beginning. Quantum mechanics with its superposition and non-locality, coursing these radically different interpretations. The arrow of time, the meaning of probability. This philosophy of physics stuff really forces you to confront the biggest questions.
It does. It pushes physics beyond just calculations and predictions into asking, what does it all mean for the nature of reality, for what we can know, for what actually exists?
So why should you, the listener, care about this dive into the philosophy of physics? Well, because it's grappling with the most fundamental picture of the universe we have. It challenges our deepest intuitions.
And it reveals how profound and sometimes profoundly strange our quest to understand reality truly is. It's about seeking truth, even when that truth looks nothing like we expected.
Which leaves us with perhaps a final provocative thought for you to chew on. If our best, most tested scientific theories like quantum mechanics lead to such wildly different stories about what's real, is there just one world with randomness, or are there countless branching worlds? Does physics give us the ultimate truth about reality? Or does it give us incredibly powerful tools to predict and engage with a reality whose ultimate nature might remain, well, elusive?
A question that sits right at the boundary of physics and philosophy.
Thanks for listening. Write us your opinion in the comments on it, Yuck. Is the weirdness of quantum mechanics an objective feature of reality or a reflection of the limits of our knowledge? Subscribe to the channel to help more listeners reach our deep dives. Thank you, and have an amazing day.